Hey everyone, and welcome. Today, we're diving into something that's literally all around us, but you probably never see it: internal flow. This is the science of how things like water, oil, and even air move through the countless pipes and ducts that are basically the veins and arteries of our entire modern world.
So, what do a giant oil pipeline and the arteries in your own body have in common? Well, you might be surprised to hear this, but a lot. They're both incredibly complex networks built to move fluid from one place to another. And the amazing part is, the very same fundamental laws of physics control the crude oil rushing through a pipeline in Alaska and the blood flowing through your own heart. Getting a handle on this physics is absolutely essential for everything from designing a city's water supply to creating life-saving medical tech.
All right, so to really get our heads around this, the first thing you need to know is that not all flow is the same. In fact, you could say that fluid moving through a pipe has one of two completely different personalities. So, first up, you've got laminar flow. Think of it as the neat freak. It's smooth, it's orderly, it's predictable. The fluid particles move in these perfect, parallel layers that never mix, kind of like soldiers marching in perfect formation. This is what you see with really thick, viscous fluids like honey or oil, or when things are moving very, very slowly. And then you have the total opposite: turbulent flow. This one is pure chaos. It's messy, disordered, and swirly. The fluid particles are tumbling all over each other in these random little whirlpools called eddies. It's like a chaotic mob. This is actually how most fluids we deal with every day, like water from a tap or air from a fan, behave. A brilliant engineer named Osborne Reynolds was the first person to really see this in action more than 100 years ago. It's a classic experiment. He set up a glass pipe with water flowing through it very slowly. Then he injected a very thin stream of dye right into the middle, and what he saw was just beautiful. A perfect, clean, straight line of dye that traveled down the pipe without mixing at all. It was the perfect picture of those orderly, laminar layers. But then Reynolds cranked up the speed. As the water flowed faster, that beautiful, straight line started to wobble. And then it just burst into this chaotic, zigzagging mess that instantly mixed the dye across the entire pipe. Those zigzags, those are the eddies. That's the signature of turbulent flow. And all that violent mixing, well, that's what creates a ton more friction inside the pipe. So this brings up a really obvious question, right? What's the switch? What decides which personality the flow's going to have? How does a fluid choose to be either perfectly smooth or a chaotic mess? Well, it all boils down to one single, incredibly important number. And that number is called the Reynolds number. Think of it like this. There's a constant tug-of-war happening inside any moving fluid. On one side, you have inertia. That's the fluid's momentum, its stubbornness, its tendency to just keep going. On the other side, you have viscosity. That's the fluid's internal friction, its stickiness, that tries to resist that motion. The Reynolds number is simply the score in that tug-of-war. It's the ratio of the inertial forces to the viscous forces. And the outcome of this fight determines everything. For a standard pipe, if the Reynolds number is less than about 2300, viscosity wins. The stickiness is strong enough to keep everything in line and the flow is smooth and laminar. But if the Reynolds number gets above 4,000, inertia takes over. The momentum is just too strong, and the flow breaks down into chaos. It becomes fully turbulent. And that zone in between, that's the battleground. It's a transitional state where the flow can flicker back and forth between smooth and chaos. Okay, this is all really cool physics, but let's get practical. Why does any of this actually matter in the real world? Well, the answer really boils down to three things: friction, energy, and, you guessed it, money. Think about it this way. Friction inside a pipe acts like a toll booth for the fluid. As the fluid moves along, friction makes it lose pressure. And to make up for that lost pressure and keep the fluid moving, you need a pump. And pumps, of course, run on energy, which costs money. Since turbulent flow is so much more chaotic, it generates way, way more friction than smooth laminar flow. And that means it costs a lot more to pump. Simple as that. So imagine you're an engineer designing a pipeline. Your goal is to keep those energy costs as low as possible. Your first thought, logically, is probably, okay, I'll just use a slightly bigger pipe. Give the fluid more room, reduce the friction. And that makes total sense.
But what you might not expect is just how huge of a difference that slightly bigger pipe can make.
Let's ask a really simple question. Let's say we've got a system and we just double the diameter of the pipe. We keep the amount of fluid moving through it exactly the same. What do you think happens to the amount of power we need from the pump?
Get ready for this. The answer is astounding. The power you need can drop by a factor of 16. That's not a typo. 16 times less energy. It's a massive difference. And it's because the friction absolutely plummets when you increase the pipe's diameter. It just goes to show you how a seemingly small design choice at the beginning can have an enormous impact on the operating costs for years and years.
So far, we've only been talking about these perfect, imaginary, long, straight pipes. But let's be real. When was the last time you saw a piping system that was just one straight tube? Never, right? Real-world systems are full of bends, valves, and all kinds of fittings that act like little speed bumps for the fluid. Every single one of these components, every elbow, every valve, even the way the fluid enters the pipe, it all disrupts that nice, smooth flow. They stir things up, create extra turbulence, and that adds even more friction. Now, engineers call these minor losses, but honestly, that name can be super misleading. In a system with a lot of bends and valves, these minor losses can actually add up and become the biggest energy drain of all. And the specific design of these little parts matters immensely. For instance, a pipe with a nice, smooth, rounded entrance is like a gentle on-ramp to a highway, super low friction. But a pipe with a sharp, hard edge, that's like a bumpy 90-degree turn onto the highway. You get way more loss. The difference in valves is even crazier. A fully open gate valve is like an open gate. The fluid flows right through. But a globe valve, because it forces the fluid through a winding, complex path, has a loss coefficient of 10. That's 50 times more friction just from choosing a different type of valve. Insane, right?
Now, let's bring all these ideas together and look at what is, without a doubt, the most advanced and sophisticated piping network in existence.
And that network, of course, is running inside you right now. It's the human cardiovascular system. It is an absolute marvel of biological engineering optimized over millions of years of evolution. The heart is the pump, the blood is the fluid, and your arteries and veins are the pipes.
But here's what makes it so mind-blowingly awesome. Unlike a rigid steel pipe, our blood vessels are alive. They're flexible, they can expand and contract. They literally respond to what our body needs from moment to moment. And as if that weren't complicated enough, the flow isn't steady and calm. It's pulsatile, surging with every single beat of the heart.
You know, any piping system, whether it's engineered or biological, works on this basic principle of supply and demand. The network of pipes, with all its friction and all its little bends and valves, creates a system demand. It needs a certain amount of pressure to push a certain amount of fluid through. At the same time, the pump, or in this case the heart, has a supply curve. It can deliver a certain amount of pressure. The system finds its balance at what's called the operating point. It's that sweet spot right where the pump's supply perfectly meets the system's demand. As we continue to engineer our own fluid systems, from massive citywide water networks to tiny little labs on a chip, it's humbling to realize we're still learning from nature's designs. The physics is universal, but the application we see in biology is just on another level. And it leaves us with this one last really fascinating question. After all our centuries of engineering, what can we still learn from the one piping system that's been perfected over millions of years?